Hello, everybody. Welcome to the lecture. So this is the fifth lecture of the Statistical Foundation for Reinforcement Learning. Um, Today we're gonna talk about RL algorithms. So we made a quick start last time, but didn't manage to cover some of the things that I meant to cover last time. But I thought last lecture was a good exercise and we covered quite a bit things to wrap up the Markov decision processes, including clarifying some of the differences in different settings in Markov decision processes and the different notations. So I thought last lecture was a nice um, that was a nice break from a lecture with more math and derivations. So yeah, I hope it was helpful. Okay, it's 103. So we'll start today's lecture. First of all, like regarding the deadline for our homeworks. So homework 0 is technically due tonight, and there are like I think many of you still haven't submitted the homework 0 yet on Gradescope. So even though we don't have a like very enforced deadline for the homework dues, but I highly recommend that you guys stick to the schedule, because that will avoid the last minute craziness when you have multiple homeworks due at the same time, and then you have to wrap them up. Yeah, homework 0 should be pretty easy, and it wouldn't take you too much time to complete. So if you have already done that, please submit it through the Gradescope. Another thing regarding the project team, so I've sent the shared Google Doc link. Um, yeah, I've sent the shared Google Doc link with a list of papers on those projects. So you should start forming project teams, and if you haven't checked out the list of papers, like maybe it's a good time to start looking, and at least narrow it down to some general area of interest. That what are the kind of subtopics in reinforcement learning that you're interested in understanding more, right? So the project is really about training you to be able to read scientific papers, and if you are more advanced, then of course you can also do something that's more interesting than that. Yeah. So it's flexible and it's up to you, and I'm here to help. I'm happy to discuss with you the specific project ideas that you have in mind. So there was a question in the chat. Are we able to get the scripts for the past lectures when they are ready? Yes. So they are already. I think lecture 1 and lecture 3. So I've received the scripts. So I'll take a closer look at them, and then hopefully I'll release them like sometime with this week. Yeah, and for those who are yeah, I'm not sure who is doing the second lecture. Um, so again, for scribes, also there isn't any form deadlines. But if you are able to send me the scribes early, then I have time to review it for you. Then the sooner you send that to me, the sooner that we will be able to make it available to the rest of the class, so everybody will have a shared document of what's going on in the lecture. All right. So that's a logistic note today. So we'll start with a quick recap before we move on to talk more about reinforcement learning algorithms. Like I said just now, in the last lecture, we talked about various matters regarding the Markov decision processes. We talked about the advantage function and the performance difference lemma. We also talked about the various different forms of Markov decision processes and what results on one could imply on another. So in this course, we'll be focusing on the infinite horizon discounted MDP and the finite horizon MDP. For the undiscounted average reward version with infinite horizon, and for those cases when we have variable, when we have the horizon to be a random variable. So those are cases that we won't be studying at all in this course. But the last lecture provided pointers for you to and keywords for you to search and figure more about those settings in the literature. and how what we learned in this class can imply results on those settings. And then in the last lecture, we talked about reinforcement learning algorithm. We focused our discussion on the principles of designing our algorithm without worrying too much about the exploration, about how we can collect the state action transitions, and how are we taking a strategic sequence of actions to maybe visit those states that could potentially have high reward. So that will be the next part of this course. So for now, we'll talk about our algorithm without worrying about their online performances, without worrying about exploration. So the two major principles behind reinforcement learning algorithm design are the model-based algorithm design and model-free algorithm design. So model-based algorithm typically involves trying to use our online access to the environment, sample transitions, and then estimate the underlying dynamics, estimate the transition kernel, XNAP with this. Sometimes by plugin, other times when the state and actions are continuous, then we cannot hope to consistently estimate this. In which case, then we'll come up with a good parametric model for the transition dynamics. And once we have that, we can do everything that we've learned from MDP by creating this synthetic approximate MDP and then run value iteration or policy iteration and so on, right? And then by the simulation lemma, then some of these techniques will result in provable learning for the actual MDP, provided that its M hat is close to M. The other family of reinforcement learning algorithms are called model-free algorithms, which they do not explicitly estimate the transition dynamics, but instead they work with value functions directly. So model-free algorithm typically avoid estimating or even representing p hats directly, but rather they use v hat to estimate the value function. They use v I guess q star hat to estimate q star directly. So these are some of the ideas behind the model-free algorithm. But the key difference from previously is that now all we have all we have access to is an online access. So the agent has to the agent has to take actions and receive the states you transition into and the reward that you receive at that moment, and then come up with an online algorithm to keep updating this v hat, right? So this v hat and q hat. And then once you have a sequence of estimate v hat and q hat, and every iterate of that would correspond to policies that you can implement and maybe apply to the next round of this interaction with the environment, right? So it's closely related to the generative model setting, but in the generative model, your sequence of observations, they're all IID. You can pick any state action pairs, and then you can query for the transition into S prime and what that S prime is and what that reward R is when you take action at any given S, right? So in reinforcement learning, the key difference is that now you have to run things online, and the data that you collect are in some sense depending on each other. So for instance, your next policy will be a function of all the data that you observed so far, and as you take actions, then those data that you collect along the while you interact with the environment, they are not really IID, right? But for now, like we're not really considering like the formal theoretical analysis of these methods, but I wanted to sketch out some of those equations behind the design of this algorithm, so that we can understand these design principles and later revisit them, formally analyze versions of these algorithms. Okay. So in a yeah, I guess we talked about MDP planning with access to generative model. We studied the sample complexity of them, and these are closely related to the model-based plugin estimator. So when they come to the model-based approaches, so many of these um, like many of these ideas from the generative model setting that we learn are more or less directly applicable. So we let's not worry about that for now. Um, so there are two categories of model-free approaches. The first is called the Monte Carlo approach. So in particular, we talked about Monte Carlo prediction and Monte Carlo control. So Monte Carlo is really about sampling. It's really about you rolling out multiple trajectories and then takes the average so that you can use Monte Carlo approximation to approximate the mean performance. And for this part of the lecture, we were following a different textbook. So this is a Sutton and Bartol textbook. So the original Introduction to Reinforcement Learning. It is not a theoretical textbook, but it is a very good textbook for us to understand the algorithms in RL and gain intuition. So there's some like notations and different notation terminologies that I didn't explain clearly last time, so I wanted to revisit them today. So when we talk about prediction and control, what they really mean is the familiar notion of policy evaluation and policy optimization. So policy evaluation is that we fix the policy pi compute. The idea is to compute or estimate the value function of pi, right? Or the corresponding Q function of pi. Control, yeah, actually, yeah, basically more or less the value function, but the Q function is once you know pi, so they're really equivalent to each other. The control is about policy optimization. So this is about how to come up with the next pi, right? So as your algorithm keeps going, how do you update your policy so that you can you can maximize your cumulative reward by finding the near optimal policy? So that's a control problem. And like if not if you're not, sometimes you're not able to get the optimal policy, but how much can you improve over the baseline policy? Yeah, so just beware of these slightly different notations and jargons. Prediction really just means policy evaluation. We want to predict the value of a given policy. And control means that we'd like to update the policy so I can control the high probability state that I visit to be those that comes with high rewards. Like another difference in the notation is that in Sutton and Bartol, the capital letter Q and V are used to denote estimates, where the lowercase letter are used to denote the true value function. Say they use the Q subscript pi to denote what we mean Q of pi, right? So this is in our notation. This is in the Sutton and Bartol book. Okay, we're not going to be distinguishing like our estimates. So when we do, we'll be adding hat to those. When we do not, then this Q and V, the meaning of them will be clear from the context. So this sometimes avoids the clutter here and there. Like one last thing. So this is actually something that both the AJKS book and the and the Sutton and Bartol book they're changing into. So previously like we talked about, the sequence of random variables are SAR, 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 each indexed by their corresponding like time index S1 A1 R1, S2 A2 R2. Oh, this is 2. Okay. But in the zero based yeah, sorry, A1. In the zero-based indexing, you start with S0, take A0, and then you receive reward R1, right? So it's a little bit counterintuitive, but sometimes this is a convenient notation. So in today's lecture, we're going to be sticking with this notation. So R1 means the immediate reward that you receive at time 0 after you take action A, right? So and now with this notation terminologies out of our way, so let's revisit how we are doing the Monte Carlo prediction and Monte Carlo control. So Monte Carlo prediction really is that we collect each episode. So we talk about the first visit Monte Carlo. And the first visit Monte Carlo of V pi of S is equal to summation of the summation of gamma to the k minus the first time index of first S, and then I guess the reward all the subsequent rewards that you collect. Okay, from 1 to yeah, I guess it should be 0. Okay, plus 1, right? To make sure that the notation is right. Right. So this is saying that the first time that you visit this state S, and then subsequently you consider the infinite horizon rollout, and then you but use first principle to estimate the expected reward. So this is what we call that. This is what we call the G. Let's say that this is also indexed by the episode I. So this is the GI. Okay, episode I. And over the multiple episodes, we can calculate the 1 over n, where capital N is the number of episodes. So we had overall is equal to sum of GI, right? So to simple Monte Carlo averages. Okay, you need multiple episodes to do this, and this gives you an unbiased estimator, of the value of this policy on the pi. Right, you can do that for all the other states and do all of them simultaneously without breaking this unbiasedness. And how about control? You can MC control. So you can do the same thing by SA equal to sum over k from 1 to infinity gamma k minus the index of first SA pair, and then the subsequent reward are all collected. This will be yeah, this will be this I guess we could also call it G tuta, and then we'll be averaging everything that we got to get this Q function Monte Carlo Q function approximation. Right. It's a silly algorithm, but sometimes it's still quite powerful because you get the unbiasedness and you don't need like strong assumptions about what your model is like. And then we move to talk about the so-called temporal difference learning. So the idea of temporal difference learning is to combine the Monte Carlo ideas with the idea of like incrementally updating your model parameter. So so we can rewrite, first of all, we can rewrite this Monte Carlo approach into an online averaging techniques with this incremental updates. And when this alpha is chosen to be some small value, so this alpha is the learning rate parameter. Typically, we think about this as a parameter that's very close to 0. So this update rule, you can think about it as a simulating a particular stochastic differential equation. And this alpha learning rate is a discretization factor of that SDE, right? So we know that as alpha goes to infinity, this is doing simulated annealing, and eventually it will converge to some fixed point as alpha goes to 0. And over many iterations, you average out the noise. And for Monte Carlo, when you choose this alpha to be something like 1 over the number of episodes, then this always give you just online averages as you get one episode at a time. And the idea of temporal difference learning is really to estimate this GT differently, right? So we could apply the dynamic programming idea by the Bellman by the Bellman equation, and then we can then we can decompose this. Yeah, I think I'm missing the expectation. I'm missing the expectation function here. Then this st plus 1 is a random variable, and the state transitions will be in there, and this becomes a Bellman equation. So if we estimate this GT using the Bellman equation, then we can plug in some plugin estimator of this GT rather than using the entire sequence. And then for instance, for this term, we can use this R to estimate. For this term, we have the random transition into st plus 1, so we substitute the actual realized st plus 1. But the issue, and then the minus s is inherited here, so you get minus s. So the key issue here is that we don't actually have the true V, right? So without the true V pi, we cannot actually get an unbiased estimator for GT. So the idea to get around this is so-called bootstrapping. So even though we do not have VT for now, can we just substitute the previous iteration of V into this equation, and then we can try bootstrapping and try to do something magical and hope that it will eventually work. And if VT is a sequence that converges to the true V, then the hope is that doing this is not something that's it's not going to lead to something that's crazily wrong. Okay, so I guess the benefit of doing temporal difference prediction is that when Monte Carlo requires many rounds of many episodes, and then the TD policy evaluation, it finishes it runs say suppose each episode is run for T steps, then in TD we've already updated the parameters for this V function for capital T times, whereas the Monte Carlo approach, you only get like one highly varying sample. And it could be nothing near the actual value function. Okay, so I hope the idea here is clear. And why is it called temporal difference? Notice that, so this is the temporal difference of this value at t plus 1 minus what your belief the value is at the time t. Right, so the difference of this is a temporal difference over the neighboring over the neighboring two steps. One more thing that I want us to realize is that suppose we so maybe it's better to explain it in the next slide. Yeah, so there's also the temporal difference version of the control algorithm. We can do TD policy optimization. And there are two main approaches for doing this. One is called SARSA, the other is called Q-learning. SARSA, the reason why it's called SARSA is because it requires the data of the format SAR S prime A prime, right? So when you have these data, which correspond to your at state S, you take action A, you receive immediate reward R, which transitions you into the next state S prime. that's not all. In SARSA, you have to also take the next action and then collect the next action according to your current policy and collect A prime, right? So this gives you the full this gives you the full SARSAR. Yeah, if you move it to the yeah, the interesting thing is that if you move it to the next R prime and S double prime, A double prime, you see that like since SARSA is updating the policy according to the updated Q function, you can see that this A prime is actually taken by the previous pipe, and this action is taken by the pi before, right? So there is a mismatch there, but for every SARSAR that you get, you can update your Q function once and then update your corresponding policy of interest. Okay, so the idea is again to simulate the Bellman equation, but now we use the Q pi version of the Bellman equation to simulate it, and we can see that we can see that if we apply the expectation to this quantity, so we will get this R of we'll get this R of S A. If we take the conditional expectation given the current S and A, we'll get R S of A plus gamma transition of Q of S prime and A prime minus Q of S A, right? So this is a temporal difference between time without prime and time with prime. Well, if you further take expectation over this A, right? If you further take expectation over the current A, so you'll get R pi plus gamma Q S A prime. This is expectation over A minus the V of pi of S. Yeah, so I guess if you take the expectation for the second term but not the first term, then you recover something that we've learned from the last lecture called the advantage function. Let us wave the hand now. So let's take its expectation of the second term but not the first term. Then this term becomes a Q function of S and A, and then we're minus the V pi of S, right? And this is the so-called advantage function that we learned before. Yeah, so the temporal difference learning is closely related to the advantage representation of the performance difference lemma, and by moving towards by changing your Q to those policies that has a bigger advantage, then we can, like in some sense optimize keep optimizing the policy as we collect new data points. Okay, then there's a so SARSA is known as a so-called on-policy method. It's on-policy because it is trying to simulate the Bellman equation rather than the Bellman optimality equation. And Q-learning are called off-policy method because it is directly trying to approximate the value iteration. So SARSA, you can think about it as a alternating between policy evaluation and policy improvement. So this step is a policy improvement, and this step is the policy evaluation step. And Q-learning, it meshes everything together by directly simulating the Bellman optimality equation. So notice that the only difference is that now we're taking the max policy with respect to the bootstrapped version of the Q function. So this is not really the true Q function. It's something that currently we are representing, but Q-learning tries to maximize that anyhow. So it has the same form of the Bellman optimality equation. So we've seen how how the value iteration approach work, the Q value iteration approach work, and we are doing exactly the same thing by maximizing some Q that's not necessarily the ground truth. Okay, the difference here is that in the Q-learning, there are more randomness in R, in S, and also in this SA. Okay, so I wanted to also highlight again that both SARS and Q-learning, so even though one is on policy, the other is off policy, both of them are online learning algorithms, online reinforcement learning algorithms, because you need to keep interacting with the environment and updating the next action using Q, using your current version of Q. For instance, you can just do greedy policy or do epsilon greedy policy to introduce a bit of exploration. So this or any other policy part, right? So technically you can still run Q-learning when you are not updating your Q function at all, right? So you can run it when you are keep playing the same old policy again and again and again, collect data. And then the Q-learning algorithm simply tries to simulate the Bellman equation when the S and A and S prime are drawn from a different state action occupancy distribution that's induced by this other policy. So that will be a case when we call this algorithm to be offline, right? So when you have a bunch of trajectories that are collected already using the policy and you don't have access to the environment at all. So that will be a topic after we'll discuss after we finish the chapter on exploration. Okay, so to quickly wrap up the recap, so they're model-free and model-based reinforcement learning algorithm. They are different really just due to what are the functions that you try to approximate. So in model-based approach, you approximate the P function using P hat. In model-free, you approximate either the value function or the Q function. So model-free, model-based. You have different space efficiency. To represent this P hat, the model-based method will need to use order S squared times A space. Whereas if you go by a model-free approach, you only need order SA space. In the functional approximation case, the differences are minor because in both of them, it depends on the dimensionality of your parameter space and the dimensionality that you're using to represent the state action pairs. And at least in the tabular setting now, the community has this like carefully studied both category of algorithms, so they are surprisingly similar to each other. And model-free, model-based approaches has a more space efficient implementations. If you design online algorithms to compute the model-based estimator, the model-free approaches they are as statistically efficient as the model-based approaches if you analyze it carefully enough. Yeah, but the differences are more significant in a large MDP setting when we need to use a functional approximation to really have some restricted estimator to this P hat, V pi, and Q hat. Okay, in today's lecture, I'm going to start by talking about a few variance improvements of SARS and Q learning. And then I'll talk about functional approximation in temporal difference learning. And then I'll wrap up the lecture with policy gradient methods. So if I don't finish the policy gradient methods, I'll teach you about the policy gradient in the next lecture at the beginning of the lecture. All right, so the first variant of SARSA is the so-called expected SARSA. So the idea is that the idea is that since we actually have the policy pi that I'm going to be using to take this action, why should I depend on the actual realized value for my randomized policy? Right? Let's say pi is a randomized policy that are given completely determined by my Q. Then I can just simulate. I can estimate this GT. I can estimate the GT differently by applying the law of total expectation, so I can get rid of some part of the variance, right? So this is by definition simply checking out the different actions different actions that you will take at st plus 1. So once you get the transition, so the expected version of the SARSA only require SARS S prime, and this A, right? So this A, I can take expectation over this A. So when SARSA is doing greedy policy updates, when pi is equal to arg max of the current Q, then expected SARSA becomes exactly the same as Q learning. Yeah, essentially this probability will concentrate around A star, which is the argmax. Okay, so you would expect that this method to work well, at least better than SARSA in practice. So this is a figure from Suta and Bartol, which run all these methods, Q-learning, SARSA, and expected SARSA on the cliff on the cliff crossing in environment. So this is environment where you are like very much like a grid world. So there's a narrow crossing. So you start here. So this is the start, and this is the end. So you can move up, down, and left and right. This is a grid world. So the optimal policy would be to just follow the trajectory nearby the cliff, and then if you do not fall off down to the cliff, you get to the end as quickly as possible, the fastest you can. On the other hand, if you somehow drop like if you somehow randomize your actions, so as in Q learning, if you take the epsilon greedy policy, then sometimes you will drop from here. Sometimes you will drop into the drop down to the cliff, and then you will you receive a negative 100 reward, and then return to the starting point, right? So Q learning because of this will Q learning because of this will have like a relatively poor cumulative reward because of the small epsilon. It keeps falling down the cliff, and then learn more information about what state is bad. SARSA, on the other hand, will learn something that will learn to avoid this situation by taking a more conservative route to the end. So in this way, SARSA can maximize its online performance, but at the end of the day, the policy that SARSA learns is not going to be the optimal policy unless we take this epsilon greedy exploration with epsilon to go to zero asymptotically. Okay, so what they compared is two things. One is the interim performance, and the other is asymptotic performance. The asymptotic performance is given by keep applying this update until it converges, say by running it for 10,000 iterations. So you see that comparing to you can see that comparing to SARSA, the expected SARSA performs significantly better, and it is even better than the Q learning. Also, if we compare the interim performance, expected SARSA is also better than also better than SARSA. Yeah. So reducing the variance in such TD learning updates usually have positive effects in how quickly that this method is learned, and also in how well that you are going to how good the solution that this algorithm asymptotically converges to will behave like. Right. So I want to say one more thing about Q learning on this example. So in the Q-learning example, you can see the sum of reward per episode is quite bad, but it is like it is still entirely possible that the Q-learning have already learned the optimal Q-star function. The issue is that the Q-learning is not really playing the greedy policy for that Q-star function. Therefore, like it has a poor online performance. Even though if you switch it to greedy, like say after a little bit of time you switch to greedy, then the Q-learning will be will always be performing the best and having the optimal optimal policy as well. Okay, so that's the distinction between on policy and off policy. So SARSAR keeps to simulating Bellman equation, while Q-learning simulates a Bellman optimality equation, whereas it might be playing slightly suboptimal policy. Okay, so another thing is an extension to the so-called to Q-learning, which with the hope of mitigating the maximization bias. So why is there a maximization bias? So if we so recall that this temporary difference term, we are using this to estimate. We're using this to estimate the reward of STAT plus gamma and max A prime, the expected value of the ST plus 1 transition from P ST AT in Q ST plus 1 A prime minus Q STAT, right? So what we are trying to get is to simulate the Bellman optimality equation, and the Bellman optimality equation looks like this once we take expectation. But what this Q-learning updates when alpha gets really small is really to move to the direction where the expectation is outside the max. Right? What it is really simulating is this instead of this. So there's a key difference. So one is expectation of maximum, the other is a maximum of the expectation. So by Jensen's inequality, we know that the E of max is always larger than the max of E. Okay, so because of this, the doing the standard Q-learning updates will have the like maximization bias. So it's also known as a survival survivor's biases, and in machine learning this is known as overfitting. So one way to address this, at least in the machine learning context, is data splitting, right? So you can split your training data into training and validation, and then use the validation to evaluate the model. So that's exactly what this double Q, the idea behind the double Q learning. So here's how the algorithm goes. So you keep track of two Q function estimates, and one we call it Q1, the other we call it Q2. And in every iteration, once we collect the data, we toss a coin to decide whether we update Q1 or update Q2. If we're updating Q1, right? Let's say that if the coin is face up, then we update Q1 using the Q-learning update. Except that the difference being we are computing the maximization using we're computing the maximization using Q1, but we're updating the parameter of Q1 using the current estimate Q2. So notice that both Q1 and Q2 are random variables. They are random variable of all the data that we have collected so far, right? So when we only update one of these parameters using using the other Q, then when we take the expectation also over these Q functions themselves, not just over the transition, then we will mitigate the optimization bias by, because now this random variable, let's say that this is A star, this A star is statistically independent to Q2. Okay, so that's the idea of double Q learning. So it can like it often works better than Q learning when the maximization bias is a serious issue. In other cases, it suffer only from a little bit of inefficiency. So basically, you're only using half of your data to estimate either Q1 or Q2. So you cannot hope to get the same statistical efficiency as if you are just using all data points simultaneously. Okay, so there are some bias variance trade-off. The standard Q learning is more biased, but it has lower variance. On the other hand, the double Q learning has larger variance due to the data splitting, but it has a much lower bias because you use two separate data to compute A star and to compute Q2. Okay, so we've talked about several different extensions to the model-free approaches, and we talk about the temporal difference learning. Like the key issue here is that when we are trying to use these methods to solve really large Markov decision processes and reinforcement learning problems, the state space is often quite large, right? So even linear dependence in the state space is often infeasible. So the next set of topics that is going to be about functional approximation. So we need to be able to learn, even though many of those states are things that are new that we haven't run into before. So for those who are familiar with supervised learning, this is a familiar story, right? So in supervised learning, we wanted to learn from the training data set, but the end goal of learning is to predict accurately on the new data that the algorithm hasn't seen before, right? So how do we generalize into this new data? It's a key topic to study in supervised learning. In reinforcement learning, things just get significantly more complex. That's because the test data, like the new environment that you're going to be running this algorithm is no longer the same environment, is no longer following the same distribution from your training data. So there's something more that we need to deal with in order for this argument to go through. Okay, so let me explain this example, and then I'll switch into a different share screen so I can show you guys a few videos to illustrate the power of functional approximation in reinforcement learning. So let's consider this simple Pac-Man environment. So who hasn't played Pac-Man before? Yeah, this is a classical game. So you are in control of this this Pac-Man, and you are supposed to move around to collect these white dots known as pellets. And there's this bigger pellets called power pellets. If you eat that, then you suddenly you'll have a period of time that you are invincible, and then you won't be touching by the ghost will not lead to end of the game if that happens. The issue about the tabular state representation is that it doesn't really capture the human's view of this game. Yeah, for instance, in the first figure, we know that this Pac-Man is in a bad situation because it is sandwiched between two ghosts. There are really no good actions to take in order to avoid the destiny of getting eaten by the ghost. However, like knowing that this is a bad situation doesn't imply anything on the situation on the right when the Pac-Man is also trapped in between two ghosts, or even this one, which is like only epsilon away from the first state, right? This is S1, this is S3. So S1 and S3, they are different only because the missing palette here. right, and nothing else. And this missing palette has absolutely nothing to do with the dire situation that the Pac-Man is in. Like therefore, we should be like with a better representation, we should be able to somehow learn like S1 actually implies both in S2 and S3 that this is a bad state, right? That we should avoid at all costs. Okay, so let me play a couple of videos to demonstrate the behaviors of this agent in the Pac-Man environment with the standard tabular reinforcement learning, the Q learning, and then with functional approximation. So let me switch to a different share screen. So just give me a second. Almost there. Are you guys able to see the share screen or no?
Yes.
You are able to see the video?
This is going to be a very...
Are you guys able to see the video or?
It's a wide screen now.
Okay, so yeah, maybe I need to do it slightly differently. Now, sorry for the technical glitch. So I'll try that again. I think the PowerPoint that's making this is slightly more complicated. I think this should work. Okay, are you guys able to see it now?
Yes.
Okay, let's try if you guys can hear the sound. So these are videos made by I think Peter Bill in the UC Berkeley.
So this is going to be a very small Pac-Man board. And what you're going to see is you're going to see a bunch of states fly by. Each state is going to have a Q value for each action. And we're going to slowly learn. So here we go. Tiny little board, we died. We died. Oh, we won. We died. We died. You mostly die. Why? Because you don't know what's going on. You're like, I've never seen this state. Let's go left. And meanwhile, the ghost is like, yum. Every now and then you accidentally eat the dot. You lose a lot of Pac-Man this way. The regret is very high. Now what I'm going to do is I'm going to let it run 2,000 times before we see anything. After 2,000 times, you've seen all these states before. You know exactly which ones are good or bad. And now you can do some amazing gymnastics and dodge the ghost. And in fact, that was a win. So you win and you win and you win and you win. What about this? This board isn't much bigger, but it just takes a long time before you find your way to that dot. And the ghost just isn't going to let you do it. And what are you learning? You're like, oh, in square 2, 3, it's kind of bad to run into the ghost. Oh, in square 1, 2, maybe I shouldn't run into the ghost. Yeah, so that's basically not going to work.
All right. So so we've seen that applying the naive state representation of all the configuration on the board to represent the state. So even though it is lossless and that completely captures the information that are needed for the Pac-Man to survive in this environment, it's if you see every state again, and then you will eventually learn. But that simply make it like too impractical for you to even run into every one of those states. Right, so if you have access to a generative model, then you can simulate the different situations by rolling out and sampling transitions from individual locations of the pellets, individual location of Pac-Man and the ghosts, and then try to roll out and learn that way. So those are the cases when you can get a linear dependence in terms of computational complexity to the number of states. But there are simply too many states for a board of say 8 by 8. So you will have say maybe 5 or 6 to the power of 64 number of possible states for you to try those, right? It's just not going to work. And the idea is that can we do something smarter? Can we represent each state using a feature vector? So here are some ideas. So we can maybe transform the state using things that we human designers of this agent consider to be useful. We can design it to be, say, the first feature to be the distance to the closest ghost. We can count the number of ghosts on the board altogether. We can add a feature about the closest pellet and the total number of pellet, and maybe some other indicators of whether something that we can compute with some additional effort, like running a graph search algorithm to compute whether the Pac-Man is in the tunnel, and so on. So these are like a vector, say a 10-dimensional vector representation that we can use to represent the state, right? Well, in this case, like different states that are like not identical may share like very similar features. So seeing one of these states having these features to be a bad state would imply that for another state that has a similar feature would also be a relatively a bad state, right? So we can derive the V function using this. We can also describe a Q function using this. So one way to do that is through this linear representation. So these are basically the inner product of this weight vector, coefficient vector W transpose of f of s, and f of s is some kind of a feature map that we can use. Like we can do the same for we can do the same for the Q function. Yeah, so this is not without loss of generality. So unlike the tabular case where it completely captures what's going to happen in the game, so such a functional approximation is lossy. So two states that are like not exactly the same, two states that have the same features may or may not actually have the same value function. So we cannot hope to use this value function to completely represent the actual value function of those states, right? But I argue often these are good trade-offs because this is a problem that we can solve exponentially faster than the original problem with a full tabular representation. And we can like we can generalize the version of the Q-learning and SARSA and expected SARSA and everything that we talked about to the function approximation case by like changing the update equation from this one, which is a standard tabular Q function, into into an update rule of those weights themselves. Right, whenever we receive a new state action transition pair, then we can update the weights of the coefficient vector by in a expression that's very similar to gradient descent. Yeah, so I'll get into it and how this exactly work. But you can see that if we're representing these Q functions as a linear function, then the linear function is completely described by this coefficient vector, and updating the coefficient vector has the same effect of updating the Q function itself, right? So then we can update the by just applying the same Q-learning rule to this setting, whereas using a parametric representation of the function, the functional update becomes simply this. And when this Q of W is linear, then that partial derivative will simply give us individual features. So what this is saying is really that if we by taking this action, then we actually received a positive reward. So that's a pleasant surprise. So in this case, I will increase those weights on those positive features, and decrease those weights on those negative features. And if we got an unpleasant surprise after taking this action, then the Pac-Man is eaten. Then I will use this update to decrease the weights on the positive features and increase the negative ones. And if you pause a minute and think about how this could work to other states, you will see that all the other states that share similar positive features that leads to a pleasant surprise will receive a higher value function evaluation when we use this updated QM value. So even if those state and action hasn't been explored before. Yeah. So among these equations, like I haven't talked about how we sample and then update this yet. So this R is actual expected reward, but you can easily replace that with the observed immediate reward, and you can replace that S prime and the expected you can replace that the expectation and the state transition by actually sample transition as S prime, which leads to the implementable updating rules to these weights. Okay, so before I start telling you guys about how this works and how this is derived, so let's take a look at what's the effect of this in the Pac-Man environment. So suppose we run Q-learning with function approximation. What is it that we're gonna be seeing?
What's nice about this is you learn so quickly from even one experience. You can learn that ghosts are bad. So what you're gonna see is a game of Pac-Man and a reasonable board with ghosts. And what you should realize is the first time you eat a dot, you get a feedback that lets you learn that maybe dots are good. And the first time you hit a ghost, you have an opportunity to learn that ghosts are bad. So instead of that kind of error and error and error, and finally after 2,000 tries, we master a 2x2 board, let's see what happens. So, dots are good, ghosts are bad. Okay. Dots are good, ghosts are bad. You see it tried to run away. And now, pretty good. Here it's not eating the power pellets. If it ate them, it would have a chance to learn that they're good if the feature functions allow that to be represented. In this case, those features aren't present.
Yeah, so you can see clearly the advantage of function approximation of the Q function and value functions is giving the Pac-Man an edge of generalizing across states. So for those states that you run into, you learn very quickly what the right action to take is, even though your Q values and Q function and V functions are not exactly the same as a true Q function and value functions. So this is what typically happens in reinforcement learning. You don't really have to perfectly approximate the value functions before that value functions become useful, right? So as long as like the right action has a higher value than the suboptimal action, then your policy of the correct value function and the incorrect value function will be exactly the same, right? So the policy could converge significantly faster than the value function converges to the optimal value function. Okay, so now I'm gonna switch back to my iPad so I can tell you a little bit of how this works. And yeah, actually before that, let's take a let's take a shorter break today. Let's take a 4 minutes break, and then we'll see each other at 12 at 2012. Okay, I'll see you guys in 4 minutes. All right, everybody. I hope everybody's back to the lecture now. So now I'm gonna tell you a little bit of about how like at least one perspective of how we should make sense of the temporal difference learning. Um, I guess we could consider this from both the tabular setting or the functional approximation setting. Okay, so first of all, what is it doing? So what is this objective function that the temporal difference learning is trying to minimize, right? So let's first a reasonable thing to think about is that now that we're doing functional approximation, we can we can no longer hope that like the value function that's represented, say, by my linear function class is going to be perfect in approximating the actual value function. So maybe like I should try to find the best approximation. So what is a reasonable best approximation? The typical the objective function that's being used is a mean square error. Suppose I want to minimize W, and W is this weights R to the D, and maybe on the some base measure of the state distribution, the actual value function of that S minus this value function of S parameterized by W. Right, so this is our approximation. So the sum over mu of S. So I'm not specifying what this mu is. So it could be it could be just one over S. It could be arbitrary distribution that you want to consider. Like in an online setting, this is typically something that's given to you in the hindsight by the exploration of the sequence of policies that you choose. Right. So the interesting part is not in the distribution of S, but I argue that for non-trivial, say the uniform distribution over S, this is a reasonable performance metric for measuring how good the approximation of W is. Okay, so now let's like we can never really observe this, but let's say that we are using the Monte Carlo approaches. Monte Carlo approach to sample. So now we sample a G. So we sample a GI in each episode. Then I can approximate V pi of S by the 1 over n sum over I GI, right? So this is something that we talked about in the recap. Okay. And then if we plug this noisy version of this V pi into this formula, then we can get this objective function, this empirical objective function, to be sum over S, and sum over I 1 over n GI. Let's call it GIS. Okay, GIS. I guess minus V hat pi S W, right? And now like let's say that we want to update this as quickly as possible after every iteration. So this n is this 1, right? So I'm updating my policy after every trajectory, after every episode. So let's not worry about this summation. Then what is the what is the update rule that I should use? Yeah. In fact, you can also keep that in there and then expand this this square and then drop a constant to recover something that's very similar to this. So the sum of square error, which I approximate according to the multiple trajectories, like I can minimize the mean square error. So what is the update rule? Suppose I use a gradient descent or online gradient descent. So whenever I observe a new GSI, then I'm updating my value function according to that. So I can just take the gradient and then run the online gradient descent, right? So what I will do is to update W into W minus the gradient of this incrementally observed GIS minus V pi S W square, takes the gradient with respect to W with a learning rate alpha, right? So when we calculate the gradient, we get minus alpha V pi S W minus my observation GI multiplied with the by the chain rule gradient of V pi S W. Right. So recall that when this is a linear function approximation, this becomes just a feature vector itself. And this minus sign, if we make it plus, this becomes plus, this becomes minus, this becomes the Monte Carlo TD estimate. Right. So this recovers something that we have seen earlier today. Right. So what if we want to use the what if we want to use bootstrapping? I argue that the natural objective function of interest is the so-called Bellman error, the sum of the square Bellman error. So we can again, let's consider the policy evaluation for simplicity. So we can try minimizing this weight vector of S. And now instead of just taking the standard difference, I can apply the Bellman equation, right? I can apply the Bellman equation to and then bootstrap, right? So I'll have this R of S, I guess on the pi, and I can approximate this since I'm running policy pi, right? I can I guess plus gamma of the expected value of V pi of S prime, right? So this is a transition on S on the pi minus my approximation, right? Minus my approximation. Since I'm bootstrapping and this term, I could also replace this with a hat, like bootstrap. Okay, so what this is a population level objective function. By sampling, we can by sampling we can minimize the square error. We can minimize the square like Bellman differences here. And by sampling, now we collect the data points S1, A1, R2, S2, A2, R3, and so on. Sarsa. And then I can instead minimize the empirical objective where this sample is replaced by this sample that I got by running policy pi, right? We can I can then get let's say that there are T such triplets, T such Sarsa observation, then I can try minimizing this R T plus 1 plus gamma V pi. Yeah, so let me add W there. So this is S T plus 1 W minus V hat S W S T. We had STW square, right? So then if we take the gradient, the online gradient descent with respect to W, we will have this update rule of W plus is equal to minus the learning rate times the gradient of this individual observation. Minus V hat ST W square, right? So then we'll get something that's similar to so what happens in the TD learning is that it's not actually like online gradient descent or stochastic gradient descent. It is actually something that's slightly different called the semi gradient method. The reason why it is semi-gradient is because in TD learning, it is equivalent to choosing this term to be fixed rather than considering this as a function of W, right? So the semi-gradient idea would drop this hat and drop this this W, and then when we take this gradient, we're only taking the gradient with respect to the second term, but not the first term. And if we do that, then we'll get W minus alpha. Yeah, let me directly make this plus. Then I'll get RT plus 1 plus gamma V ST plus 1 minus V hat ST W multiply with the gradient of V hat ST W, right? So when then this gradient will just becomes the features of the state in the linear case, right? So you can check that this is a temporal difference. So this is a TD error delta. And then this recovers the TD prediction rule with function approximation, and we're moving towards the direction of updating the coefficients by the that's proportional to the feature vector, and depending on whether this TD error is positive or negative, and it is incrementally correcting these weights so that so that the hope is that we're minimizing something. Because this is not a gradient step, then it doesn't directly minimize the objective function that we have in mind. But the semi-gradient method is a viable method on its own right, and the Sutton Bartle book provided some intuition why this method could actually work, and why it also converges to something that's meaningful. So let's try making sense of this semi-gradient method. So let me simplify the notation a little bit. So let's say that the semi-gradient method update the W by adding a little step towards the gradient direction. So first of all, I'll define this XT to be the feature map of ST. I'll define yeah, so similar xt plus 1 will also be the feature representation of t plus 1. So I'm just using this as a shorthand to denote the feature expression. So now I'll have this update step of RT plus 1 plus gamma W T transpose xt plus 1 minus WT transpose xt multiply with this gradient, and the gradient is xt. So this is a semi-gradient updating rule. And then let's try to make sense of this by considering very small alpha. We can consider very small alpha and many iterations, and then try to find the fixed point of this iterate, right? So what we can do is to take the update over and divide alpha on both sides, and then we get RT plus 1 multiply with XT plus gamma I can extract this WT. I can extract this WT out together, and then I can basically swap the order of this this inner product, and then like move W to the right hand side, so that I end up getting a matrix vector multiplication. So what that is x xt multiply with gamma xt plus 1 minus xt transpose and multiply with WT, right? So with this manipulation, I can make that. And when we take alpha to go to 0, and this increment is also getting smaller, so we are getting the derivative of this W, or the gradient of this W is equal to R t plus 1 xt plus gamma xt. Wait, yeah, I don't think I have gamma here. Xt gamma xt plus 1 minus xt transpose. So this is a matrix multiply with WT, right? So now let's take expectation on both sides by conditioning on WT. T plus 1. Yeah, if we condition on WT, then we get this reward of based on pi multiply with xt plus the expected value of xt. This will be the expectation. Yeah, I'll just put the expectation together. Gamma xt plus 1 minus xt. And these expectations are over the data that we collect in order to construct this TD update rule, right? In order to construct this TD update rule, and these are these random variables are those states, are those SAR, and these corresponding feature representation xt and xt plus 1, and also this received the reward function, right? So what we have constructed is that the gradient, yeah. So the gradient of this W in expectation. So as alpha goes to 0, this is like keep simulating everything, and when does this W remain where it is? So this is when the expected value is actually equal to 0. When the expected changes is equal to 0. So assigning this to 0 means that we want to derive its fixed point. So what is this fixed point? So we can call this matrix. So notice that if X is in RD, so this is our D by D matrix, multiply with that. Yeah, let's call it minus A, multiply with WT. So this is minus A W, and this is a vector. This is a vector in R of D, and we can call it this B, right? So when this is equal to 0, it says that AW equals to B. So it is a linear system of equation, and we can derive the fixed point of this temporal difference updates with the semi-gradient methods to be A inverse B. Right. So in some sense it does converge. It is simulating a particular stochastic differential equation, and when alpha is small, then it is converging to converging to something that looks like a closed form solution of in some sense simulating the function approximated version of the Bellman equation. Okay, so I guess like this realization also provide us some like additional insight on how we can design better algorithms with lower variance. So that brings us to the least square temporal difference method called LSTD. Okay, if we're like so far the TD methods that we're doing the sampling, and then once we have sampling, we construct the stochastic approximation of the Bellman error, then we're moving a little bit towards the direction of the Bellman differences, and together with a gradient of the function approximation. So LSTD says that like if we collect all the data so far, then we can just directly use this formula and directly calculate the optimal solution without iterating. And in every iteration, it corresponds to just updating this A and updating this B, and then solve this linear system again. So that will get significantly more stable because we will no longer be suffering from the high variance due to the state transition and due to the immediate reward observation. Okay, so the idea of LSTD is to use use this formula and then try to replace A with A hat and B with B hat, where A hat where we simply replace it with an empirical observation k from 0 to t minus 1 and xk. So recall that this is a formula that we have for A gamma xk plus 1 inverse. And in order to make it more stable, so sometimes we add a little bit of regularization term, like a little bit of smoothing term to ensure that this A matrix is invertible. And B hat. B hat would be, again, summation from k from 0 to t minus 1, and then I'm using the observed reward, right? K plus 1. Recall the shifting of this reward by 1 in Sutton-Bartle notation. So that's the reason why this is rk plus 1. And then I can get Wt in the intermediate steps of this least square temporal difference learning to be the A hat inverse of B hat. Yeah, AT hat inverse of DT hat. This will be the update rule. So in every iteration, we are basically adding this this term to the design matrix and adding an additional term to the B hat matrix, right? So space is d square, is order d square, and incremental updates is pretty cheap too. Like solving this linear system of equation in the worst case would take OD cube. When d is small, this is not an issue. But there is a computational trick that everybody like should know. Is to use a so-called rank 1 update. Rank 1 update of A inverse, right? Of A t minus inverse into A t inverse, right? So the trick behind this this algorithmic tool is the so-called matrix inversion lemma, or also known as Morrison Woodbury identity. Yeah, sometimes even Sherman Morrison Woodbury identity. So the specific update rule is so this is the same as A hat t minus 1 plus x k minus 1 xk minus 1 minus gamma xk t minus 1 xt transpose inverse, and this can be, you don't have to explicitly calculate this inverse. This can be rewritten as AT hat inverse minus AT minus 1 inverse. You can simply like use Yeah, notice that if you already know how to compute this at minus 1, then you can end up like needing to solve only matrix vector multiplications rather than inverting the full d by d matrix. Minus gamma xt transpose a t minus 1 hat inverse x t minus 1. Right, so that would be the formula. So notice that everything can be computed in order d squared times if you use this matrix inversion lemma. Right, so yeah, so that's all I wanted to talk about as a variance of the functional approximation. So far I've talked about the model-based approaches for and also the model-free approaches, including the Monte Carlo methods and temporal difference methods. And then I talked about the linear functional approximation in Q-learning. I've shown you that the idea behind the temporal difference learning is to minimize the mean square error in your approximation. And when we use bootstrapping in addition to that mean square error minimization, together with somewhat hacky step of defining the semi-gradient update rules rather than the gradient update rules, then we can define the temporal difference learning. Yeah, we can define the temporal difference learning. And the temporal difference learning with the semi-gradient method, it converges to a slightly different point than the one that minimizes that minimum Bellman error. Yeah, but because of that and due to the simpler update rules, then we can come up with closed form solutions to the TD estimates, especially when especially when we are using the linear functional approximation. So by the way, this equation also tells us that it converges to a unique minimizer, right? Because setting the gradient to 0, and this is the only points where this is only points where in expectation this semi-gradient TD methods would converge, right? And as long as A is invertible, so under weak conditions, you can show that this is invertible. So whenever this is invertible, then so there's a unique solution that TD is converging to, right? In terms of how good this solution is, this is a separate question that is still being studied in various different settings. Okay. So the next thing to consider is that what is a corresponding policy class? So far we've been talking about approximating the value functions and Q functions. Are there other ways of parameterizing the problems and doing functional approximation that could have a different set of characteristics? So I only have like 10 minutes left. So I'll briefly talk about what policy gradient methods are, but I'll probably have to leave the policy gradient theorem and the proof of policy gradient theorems and various extensions to the next lecture. Yeah, so let me tell you guys about the ideas of policy gradient methods. So we've been using the function value function approximation by V hat to approximate the V pi function, and Q hat to approximate the Q star function. And sometimes these are parametric, right? So these functions are given by a parameter vector, right? Parameter vector W. In policy gradient, we can I guess like once we have these functions, in particular once we have Q functions, and then it induces a corresponding greedy policy class where indexed by W as well, which contains the policy that take argmax of this Q hat W. right? So whenever we specify a Q function class, it induces a greedy policy class. It could also induces epsilon greedy policy class. So there are families of policies that we can derive based on our value function approximation. On the other hand, like we can directly parameterize a policy class. So we can directly parameterize a policy class with theta, which contains a bunch of policy theta that maps state to a probability distribution on the action space, right? So whenever we fix theta, then we get one policy, and as we update the theta parameter, then we get a different policy, right? So this is nice because then we can potentially run gradient descent style incremental learning algorithms directly on the policy class without worrying about modeling and approximating the actual value function. So I'll give you a few examples of these. But by the way, for the for the policy gradient part of the lecture, we'll be following both the Sutton and Bartle book and the AJKS book, right? So both of them have good coverages of the policy gradient style algorithms, and yeah, sometimes we'll be referring to SMB, other times we'll be referring to the AJKS. Well, I'll give you a few examples of such policy classes. So the first example for the tabular setting, when the state and actions are both finite, I can define a simple softmax function class. So policy class where the pi of theta. So in this case, the theta is in the space of S times A, right? I can define a softmax function class to be e to the power of SA, e to the power of theta indexed by SA over the A given S, sum over A prime exp theta SA prime. Okay, this will always be a probability distribution over A due to this normalization, like this theta is not necessarily the value function because it's not bounded at all. It's not bounded between 0 and 1, or a 0 and R max, or whatever way we constrain our values function to be. Like this is just an arbitrary real value theta. And in the linear feature setting, so in the linear feature setting, we can consider the log linear policy class using the same logs using the same soft argmax transformation. We can say A of S to be exp of theta transpose of F of S, where F is some kind of a feature map, right? And then now, some feature map of SA pair, and then I can add over A prime by dividing this by the normalization constant, and that gives me like similarly a probability distribution and a particular policy that the algorithm can follow. Right. So more generally, we can consider the nonlinear function, function class. This was called by AJK as a neural policy class. Neural policy class where pi of theta A given S is simply the soft argmax transformation of some feature transformation indexed by theta. Then I normalize itself F theta S A prime. Okay, so the only requirement typically for this function class is F of theta is differentiable in theta. right? In which case, like you could already apply policy gradient idea. Yeah. So I guess so this slide will be the last slide of today's lecture. So once we specify a policy class that's parameterized by parameters theta, then we can hopefully optimize a policy directly by running SGD, right? So the idea is that we want to minimize theta minus the value minus the value of pi theta starting from mu, right? So this is using our notation of value function, and this is a little bit to, this is equivalent to minimize minimize a negative value function. So it's the same as maximizing the actual value function. So this will be the expected value of the sum over t from 0 to infinity r t plus 1 when all the actions are drawn according to the when S1 is drawn from mu, from S0 is drawn from mu, and all the subsequent actions are taken according to pi theta, right? So this is a like stochastic approximation problem, because the objective function is an expectation, and we do not necessarily like know what this value is, and we cannot have access to its actual value or the gradient. But we can approximate it by rolling out, right? By rolling out, we can approximate by replacing this with some sampled trajectories of sum over r t plus 1 I, right? And this is only approximating the objective function, and then theta is not even parameterized there. But if we can use some other approximation, with theta, or we can directly approximate the gradient. We can take the gradient of this v pi theta mu. If we take the gradient of v pi theta mu, then we can update the equation by running stochastic gradient descent. If we can somehow approximate the gradient there, then we can update theta by theta minus plus, because of this minus sign here, alpha times the gradient hat v pi theta mu. Right. So in order to run this, all we have to do is to somehow use the rolled out trajectory to come up with a stochastic approximation of the gradient, such that the expected value of is equal to the expected value of this at theta, conditioning on theta, is the same as the actual gradient of v pi of mu. Okay, so we'll talk about how we can construct such estimates in the next lecture.